Hello and welcome to today's video. Today we're going to be taking a quick look at the I2C interface, in particular how to connect multiple devices to the bus. So if we start with taking a quick look at the schematic or the circuit diagram that I'm going to be using today, you can see on the left we have the Arduino Nano. Now on the Arduino Nano, pins A5 and A4 are used for the I2C interface. So A5 is the SCL, which is the clock line, and A4 is the data address line, SDA. There's only a few things we need to be careful of when using the I2C interface. The first of which is choosing the voltage. Now obviously you want to choose a voltage that all of the I2C devices can support on the bus. It is possible to use logic level converters if you have to, but if you don't have to, then it's easy just to avoid it. In my situation here, I have 4 I2C devices. 3 of the devices can support 5 volts, but all 4 can support 3.3. So it makes sense for this project to set the I2C bus to 3.3 volts. Now the next thing to remember is the I2C bus, the data line and the clock line must be pulled high using a resistor. Typically the resistance value is between 4.7k and 10. It's not particularly critical. In my situation I'm using a 10k. Now one thing to be careful of is some of the modules that you use may already have their own pull-up resistors, in which case if you add an extra pull-up resistor, then you're actually lowering the pull-up resistance. So it's important to check the modules that you're using that they don't have pull-up resistors, or if they do, that the combined resistance is still greater than about 4.7k. You also have to be careful to make sure that the Arduino Nano isn't using its own pull-up resistance. The reason we need to pull up the resistance is I2C is an open drain system, so that when a device wants to send a signal, it pulls the signal low. Okay, so if you don't have the pull-up resistors there, it won't be possible for any of the chips to send any signals whatsoever. The final step with the I2C interface is the speed. Now we're talking about the voltage and the pull-up resistance, but the speed is the next critical thing. By default, I2C started off as a 100 kilohertz speed signal. Now with progress they've gone into fast and high speed. Fast is around 400 kilohertz. High speed is anything above that, anything from 1 megahertz up to even 5 megahertz. In practice, if I needed a faster signal greater than say 400 or 800 kilohertz, I probably wouldn't be using the I2C interface. I would switch over to using a more robust interface. But for everything which we're going to be doing with this project, 400 kilohertz is plenty fast enough. Now the only thing to be aware of when playing with these modules is the actual speed, maximum speed supported by each module. You don't want to set a bus speed faster than the slowest module. So out of these 4 modules, the I2C interface to the EEPROM can run up to 1 megabit without any issue, but the display, the real-time clock and the atmospheric sensor really max out around 400 kilohertz. So in practice the fastest we would want to set the interface to would be 400 kilohertz. If we wanted to talk to the EEPROM at the faster rate, it's advisable to set up a second I2C interface rather than trying to change the speed when you're talking to one of the chips. The reason for that is reliability. If the other 3 modules cannot operate at that speed, then it's not deterministic. how they would react when they see a clock signal with data going through at the higher data rate. Now I'm going to leave the video there with a little bit of a teaser, just showing you a demo script that I have. It's an electric dice project. I'll be showing you how to get started with this in the next video. Thank you for watching.